So what I want to do today is I want to talk about the nature of data and variables. Last class was more about what is social science and how are statistics going to help us with that. Today is how we as researchers need to start thinking about collecting data and what shape that should look like. So let's start with a very simple definition. Data is a collection of variables. Variable is anything that can take on a different value. So variables vary. And they are not a constant. So let's think of a variable that we can measure about people or institutions or anything. Should be an easy question. GPAs. Because GPAs can take on different values. Absolutely. Give me another one.
Average gas price.
Gas price. $2.49 this morning. Anything else? Give me another one. All right, income. You got it. Give me one more. I want somebody to give me a bad one so I can say something mean to them.
Price of blue shirts.
The price of blue shirts. Bastards. And I walked right into that one today. Just for the record, my shirt yesterday was blue and white. All right. Somebody give me an example of a variable that is constant. Therefore, not a variable. That people have heard of and would know. And when I say it out loud, you all will smack your foreheads and go, "Oh, I can't believe I didn't know that one." You ready? Get your pen out of your hand.
No, ounces in a pound.
Nope. What's that?
Pi.
What is pi? All right, I'll let you stop there. Don't want you to look bad. Pi is a constant. Pi is a magical number. Why is pi a magical number? It's great. It's a fraction that never ends. The remainder of pi goes on so far forever. We've calculated, there's actually a race in math to find the end of pi. They haven't found it yet. We're talking billions of digits. When does a fraction end? When do decimals end? Right, when you get a long string of zeros and you just keep getting zeros. Because remember when you were in school and you had to do that remainder thing? Yeah, when you get the remainder to be 0. The other neat thing about pi is all of these digits, they don't repeat. So you can't find like a pattern in, you guys do not care at all about this. This is really one of those magical things about math that you just have to, come on. All right. So pi is a constant. There's another famous constant that nobody really knows what it is. But hopefully you've heard of this. E equals mc squared. Anybody know where that's from?
Einstein's theory of relativity.
Okay. The energy of matter is equal to its mass times a constant squared. That constant is? Yeah. Speed of light. 6 point something something times 10 to the 8th. Oh, a black hole is a dense thing. That's more about density. I don't think so. But we do measure things in, like theoretically, we can measure things in speeds of light, like in C's. Fun nerd fact, in Star Trek, when they talk about warp drive, warp is actually the speed of light. So if you go warp 10, you're doing 10 times the speed of light. But we can't even get enough energy really to be the speed of light. And it's kind of a misnomer because light is both a wave and a particle, so it's weird. All right, so speed of light is a constant. No, we haven't found anything that goes faster yet. But theoretically, maybe. Okay, so that's a variable and a constant. We don't deal with constants because constants make horrible data. It'd be like asking you, what is your planet of residence? And hopefully, everybody here will say, thank you. Everybody will say Earth. Okay? You just get a data set with a string of Earths going down. It's not a variable. It's not a good variable. Is your respondent alive? Hopefully they all say, yes, we're alive. That's a constant, right? Okay, so we're clear on what a variable is. What shape or what form our variables take is a question that sometimes is up to the researcher. So I'm going to go in like order of giving us information. One type of variable, and I think the best type of variable, is one that is measured in a continuous fashion. Continuous variables, in theory, up with air quotes, are infinite. Oops, wrong way. They can range from negative infinity to positive infinity, in theory. Also, we should be able to have, depending upon how precise we are, infinite measurement in between our values. So this is where that pi thing comes in, right? 3.14, and away we go with the decimal points. That's in theory. Because in theory, it's infinite, anytime we measure it, it'll always be an approximation. We'll always sort of say, all right, this is, pi is 3.14, and we're going to leave the rest of it off. That's an approximation. Right? We're going to say we're going to use 2 significant digits after the decimal point. That's our form of measurement. Can you think of something that would be measured in a continuous fashion? Not definitely, but kind of like continuous. A range of many, many values. Did I forget the question mark? Give me an example of something that is approximately continuous. Okay. That's a count variable, though. Right? Because can you have negative galaxies? Okay, so let's not go there. Temperature. I like temperature. Why temperature? Okay, there can be negatives, which is a good thing. So if we make this Fahrenheit, we can have negative degrees in Fahrenheit. And we can have positive degrees in Fahrenheit. Actually, let's simplify this. Let's do Celsius. Because 0 Celsius is what? 32 degrees Fahrenheit. Why is that notable? It's the freezing point of water. So we're going to measure the temperature of the air based upon the freezing point of water. Perfect sense. All right, so let's just call this hot and cold. Can we get infinitely hot or infinitely cold? Why can't we get infinitely cold?
Eventually you just reach a zero point. Like the stuff that makes things hot just stops.
Okay, but can we ever get there? No, because you can't have anything colder to take the energy away from something that's nearly frozen. So absolute zero is a concept, right? We can get to it, but we can't. We can slow molecules down. We can get really, really close to absolute zero, but because you can't get beyond absolute zero, you can't have that be the cold thing to make the really cold thing really colder and stop. It's not a heat sink anymore. Okay? Idea of how hot we can get. I don't know. Let's explode some stars and see what happens. Okay? But temperature has a very, very large range. So temperature is a sort of, let's just call it continuous variable. All right? Give me another thing that's may not purely be a continuous variable, but approximates one.
So it has to have a negative.
I really want it to have a negative. How so? Right. Debt and wealth. Okay? You can go into the negative. In fact, if anybody in here has a wallet, you have in your wallets negative money. I can guarantee it. You got a wallet? Can I have it? Temporarily? Can I borrow it?
There's any money in there.
Well, let's see. No. Okay, he has, let's say, $2 in here. But the value of his wallet is less than $2. How? Okay, so if you have credit cards, you have credit, which is future debt. Okay, so let's say the limit on his credit card is $10,000. Here's negative $10,000 right here in my hand. Ooh, shiny. Okay, thank you. All right. With inflation and how we measure money, we could make these numbers really, 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 really big if we wanted to, right? We could devalue, we could change the value of our currency and multiply everything by a million. So dollar bill is actually $1 million bill now. We can do that. All right. So we can fudge the numbers a bit. One of my favorite episodes of Top Gear, they drop the guys in Vietnam and they hand them a shoebox full of paper money. And their task is to drive from the south of Vietnam to the north of Vietnam. And they're like, we have money. And they go to buy it and they realize that their money, their shoebox full of paper money in the millions is actually worth like $200. And they're like, but I have all this money. And it's great and it rains and they like don't care about the money anymore because it's not really valuable. All right. So you could do that. We can change our base of our currency. Continuous variable. Lots of range. The other type of variables are known as discrete variables. And discrete variables are different because between any two values is absolutely nothing. So in our continuous model, when we were talking about dollars, what's in between $1 and $2? 99 cents. Okay? Or 101 cents if you want to count the zeros. Okay? Continuous has that infinite space in between where there's room. A discrete variable has no room because there's nothing in between them. So your values can be only whole. I have 2 and only 2 children, John and Abby. I do not have 2.3 children. Because as big of a pain in the ass as my cat is, it is not worth 0.3 of a child. Because they do not come in increments. I have 2 half-brothers, so does that mean I only have 1 whole brother? No. I have 2. Okay? So when we count, it is whole units only. It is an exact measurement. 2 children, 1 and 2. And there's no real need for an approximation. Like, I got some children. I got 2-ish children. No, I have exactly 2 children. Now, these variables can take a few different forms. Nominal, ordinal, or dichotomous. And we'll walk through those next. But are we clear? Discrete means whole numbers. Start with nominal. Nominal variables are more like names. See the N, think names. Names of groups, perhaps. Like a religion. And what we do with nominal variables is we try to classify and put into groups. Another fun fact, you know what the scientific name for putting people into groups is called? Discriminating. That's what it is. To discriminate is to put people into groups, scientifically. In society, we actually think that's a bad thing, right? It's bad to discriminate. Well, when you're classifying people into categories, it's known as a discriminant. Discriminant analysis. Do the categories fit? So we can name the categories, and we can pretty much have as many categories as we want. You heard of the Pastafarians? Has anybody heard of Jedis? Because there are people in other countries that say that they're Jedis and want it like listed on government documents and when they fill out their census and stuff. Mostly British people. Okay. There's a bunch of interesting folks that live in the Kentucky area that like to put up monuments to Satan. Kentucky, Alabama, like places where you would think people want to put up the 10 Commandments. There's also a group of people that are like, me too, and they got some goat-headed thing. And they're like, this is my God that I worship. Now, how do we take these classifications and turn it into data? Easy. Just put a number. Any Catholics in here? All right, Catholic, what number do you want? No, you should want a different number. What number should the Catholics really want? You should want 3 for the Holy Trinity. All right. See, and this is where it comes in bad. Like when you think you're assigning the number not based upon just giving them a number. Like, oh, we're the best. We're number one. No. Right? These categories are just there to have a number represented in a data set. 19, 57, 8, 27. Give the Satan worshiper 666. Okay. Actually, what is the number of Jewish people like? Isn't it like 6 or 8? I don't know. All right. We got to bring balance to the force, too. Okay. The numbers don't really matter. They're just the number that you used in the data set to represent that group, so that all the people that say they're Catholic in the data set get the same number. Okay. So when you look at a code book, you might go, why did this person or this group get this number? It literally doesn't matter. Then there's no convention on this either, where you think, oh, we'll put them in alphabetical order, or we'll put them in the order of, the most number in a group. There's really no convention to it. You just got to assign it a number so that you can quantify it and put it in a data set. Ordinal, again, classifying into groups. But the groups are actually in a order, some sort of ranking system. And we're used to seeing these ordinal rankings. This is a standard 5-point scale. We want to ask you about your instructor. We'll give you a sentence and ask you to either, Professor Wood is a sharp dresser. Do you strongly agree, neutral, disagree, strongly disagree? Right. And you can choose usually on a 1 to 5 scale. The order of the numbers should match the order or the degrees of the ranking. You can also either make this bigger or smaller. Let's say you want to lump the disagrees together and the agrees together. Let's say you want to go in the opposite direction and you think there should be a slightly. The only thing you should make sure that you do is reflect both sides. Last weekend was the American Political Science Association's annual meeting. We call it APSA. It was in San Francisco. And after APSA, they sent out a survey. And one of the survey questions was, APSA 2017 met or exceeded my expectations. So you had two options. It either met or exceeded. Well, what are they missing? Did not meet. APSA 2017 sucked. That was not an option. And it's like, hey, political scientists, do you not have somebody in the room that can teach you how to have an odd number of responses? Because it's kind of important. You have to have both sides of the continuum. So that's an ordinal variable. Finally, the simplest and easiest and my most favoritist variable is a dichotomous variable. Dichotomous variables have other names. It is a binary variable. What values do binary numbers take? Come on, I need a nerd to tell me, what are the two binary numbers? There we go, 1 and 0. Or my favorite, these are also known as dummy variables. Because if you don't understand this, you're not so smart. These type of variables are measuring one and only one trait or characteristic. Dummy variables are like a simple light switch. The lights are on, the lights are off. The lights are on, the lights are off. It is not a complicated light switch, like this stupid thing. There we go. All right. Okay, 1 for on, 0 for off. When you create these dummy variables, you should name it the presence of that trait. So to be male, what value would having a penis get you? No, what value, like data number, would it give you? A 1. If you are not male, and that can include all of the other things that people are classifying themselves gender-wise, female, cis female, transitioning female to male but not yet male, right? That whole long list of how we can create different genders. If you're not considering yourself 100% male, it's a 0. Now, if you want to have other classifications, you create more variables. And you come up with something that is 1 or 0. And you got to have a classification scheme that gives you a clear choice between one category or the other. That classification scheme usually involves the creation of a cut point. Because it doesn't have to be a binary phenomenon. But you have to come up with a decision rule that allows you to say you're either this or you're not. Old. At what point does a person become old? You think you're old? You're 26. Is he old?
No.
No. You're not old. 70. Is 70 old?
Yes.
Yes. Is 69 old?
Yes.
Okay. She says no. You just said 70 was old. I didn't say 70 was old. You said 70 was old. Okay. You, as the researcher, when you're creating variables, you have to sort of justify how it is that you are creating these decision rules or why you're using this cut point. So she said 70 is old. He said 26 is old. No. On or off? Old, not old. Now, you don't have to be young, right? It doesn't have to be old and young, because that's more of a, what kind of variable? No. More of an ordinal variable, right? So you, as the researcher, have to sort of justify this. Now, here's the great thing about these variables, is for the most part, you can take lots of information and simplify it. Oh, I should pick a blank one. Here, this is pretty blank. So one of the variables that you all mentioned beginning was income. And we can measure income continuously. right? And we can just use the actual dollar amount. We can also measure income in an ordinal fashion, and we can create categories like stupid rich, rich, well off, middle class, lower middle class, poor, destitute. And in order to do this, we then need to come up with some ranges, right? Well, what makes you stupid rich? So rich you can be completely stupid and get through life. I don't know, 100 million? 20 million? 50 million? It's got to be something million, though. All right, 50 million. And up. Rich, let's just say you got to be a millionaire.
5 million.
No, you got to be a millionaire. 2, 49, 99, 99. Okay? And we can go on through and do this, right? Or we can also create a dummy variable. We can take a whole range of dummy variables, right? We could say you're well off. Well, you're well off if you're anything from the cut point for well off and up. And if you're under the cut point for well off, then you're not well off. So well off would include rich, stupid rich, and well off. You got that? Because it's this cut point and up. You as the researcher get to do this. Because you get a data set and it has actual income by dollar, and you say to yourself, it's great that I have this by dollar data, but what additional value do I get by learning of a $1 increase in somebody's income? It's really not helpful, right? So you might take that continuous data and you might change it. You might do it in thousands instead. But still, what's the marginal return on a $1,000 difference? So it might be that creating categories is helpful for you to understand the difference in the public health views between the stupid rich and the destitute. The book uses pretty similar terminology, but there's two differences that I just want to mention. The book talks about nominal data, we have that. They talk about ordinal data, we have that. They don't really talk about dummy variables, and they don't really talk about continuous variables, but they do talk about interval variables and ratio level variables. Interval level variables, values are equally spaced on a numeric continuum. That's a lot like income. Right? Each dollar amount has 99 cents in between it. It's a continuum. It can go in positive and negative directions. So their interval is more like our continuous variable. And they also include a ratio variable, which are interval variables with a true 0 point. GPA is a good ratio variable. It contains the 0 point. You fail all of your classes, your GPA is 0.00. I met that kid before. Actually, I met a few of those kids. The guy I went to college with was a drug dealer named Stapleface. Because he had a bunch of piercings. You got it. What was his... Well, so his first semester he was there, he got a 0.0, and then he appealed his 0.0 because he tried to get one of his classes changed into an incomplete so that he had a potential GPA if he resolved the incomplete. And I think they let him back, and then I think he failed out again. So, yeah. Well, not so good if you're not around a bunch of college kids. All right. Mid-90s. This is 20 years ago. All right. So when the book talks about it, I want you to be aware of a little bit different language. I've been trained differently, and I use different terms. I'll do my best to adapt to the book, but I'm sorry, but you just have to know what a dummy variable is, because they're the easiest variables to create. Now that we know what form data can take, I want to talk about and comment on some of the stuff that the book tells you about how to visualize or examine this data. And practically, the best way to look at data is in a table. And so the book shows you what a frequency distribution table looks like. This is it. Okay? You count up the number of times that you observe that category or that value, and that's F. F stands for frequency. So this is something about lottery tickets and how you choose lottery ticket numbers. Do you use random numbers? So you walk into the store, you hand them 20 bucks and say, "Give me Powerball." And they're like, "What do you want?" And you're like, "I know nothing about this. I'm only playing the 20 bucks because it's over 500 million. Give me the Powerball." And they're like, "All right." And they literally hit a button, and it gives you a randomized set of numbers, which is fine because the selection method for the balls that they pick out of the Powerball are random, so you're okay. It appears that from this data, that's how most people, 54% of the sample, play the lottery. Random numbers. You have people that use a sequence of numbers. Okay. They look for patterns. God bless my mother. She's a pattern person. New York has this thing called Quick Draw, and every 5 minutes it runs the lottery. It's like Keno in Vegas. 80 numbers, you pick 5, and the more of the numbers you get, the higher your payout is. I wish she would just like hand me $5 and I'll tell her whether or not she won or not. Like, "No, sorry, you didn't lose. You want to play again? We can play again in 5 minutes." And then she'll hand me $5 and I'll be like, "Oh, you won, here's $2. And we can just do that all night. Because it's completely random. But my mom says is no, if you play 34, you also have to play 44. Because 34 and 44 come up in pairs. Oh, Mom, let me teach you what random means. Okay. Or people with a pattern like birthdays. You got to play 27. You just have to. 27 is a magical number in my family. So play 27. And 4, because it's the other part of 27 in my birthday. So 4 and 27. All right. And it was Abigail's birthday. She was born on the 4th. So you really got to play 4 too. All right. This is a great way to visualize the data. It tells you the number of times it appears in the data set, and it also gives you a relative number. What percentage of the data set is it? So I can quickly see that first place, most people do random, and I can use that word most because it's a majority. Then pattern, then non-equilibriated, whatever the hell that means, and then finally a sequence of numbers, which is pretty rare because only one person out of the 22 did it. That's a frequency distribution table. These things are handy. They're a great way to report what your data looks like. This I agree with. This I disagree with. Goddamn bar charts. What's wrong with bar charts?
Misrepresent values based on the X and the Y.
We'll get to that. That's more of something else. But what's wrong with a bar chart? they can look better. But you know, we're not those type of people. We don't judge things by their looks. You know what's wrong with a bar chart? It's not a frequency distribution table. The whole point of a bar chart is to display information. And anytime you got to take your bar chart and you can't easily get the information from that, you got a problem. How many people use the sequence method? How do you know that? Because it's a number in between 0 and 2. You know how I know that one person uses a sequence? Because it actually says one person uses a sequence. How many people use random? Are you sure?
Yeah.
Well, let's check. This actually says 12. How do I know it's 12 over here? God damn it, I need a thing. I gotta go over here. Oh, I got a touch screen, so this is gonna be really hard. Phew. I hope that's right. All right, you remember this? You have to sit there and you have to draw the stupid lines over. And fortunately for us, the scale is pretty good, because if it's in the middle, it's 1. But what if this was by 5? Oh, we'd be really screwed, right? Because then I got to go, okay, 1, 2, 3, 4. Oh, I put the 4 too close to the 2. Son of a bitch. Got to start over again. Erase it, and it gets all messy. These things are wrong. Don't do this. Just do this. Right? It gives you the exact thing you need. And you have the ability to compare sizes via a percentage. Because 54 is about what of 27? About double, right? Twice as much. And 27 is about what of 14? It's almost double. All right? I can also just look at the numbers. This is double of that. That's double of that. Ain't nobody in hell doing this. All right? I don't have to know that sequence is the lowest by saying, oh, look, it's the shortest bar. All right? Don't do bar charts. Bars represent frequency or percentage of each value of the variable. Yeah, so do frequency distribution tables. In number form. Don't use bar charts. And if I'm not going to let you use bar charts, there's no way in hell I'm going to let you use a pie chart. Because what don't pie charts give you any information or ability to know?
Actual number.
The actual goddamn number. I know that it's 5%. 5% of what? This is a piss poor pie chart because it doesn't tell you the overall n. 22. So now I gotta go, oh shit, what's 5% of 22? Well, it ain't 1, because I've rounded up. So don't do this either. The other problem with pie charts is you try to like get all cute with the colors and it makes my eyes bleed. Like here they did a shaded gray, you know, well this is this different gray and they got this gray. And then some of them come up as like, you know, the colors of the Olympic rings. I got a yellow and I got a white and I got a red and I got a blue. They just look awful. They're designed to give you an idea of relative size. So that this random slice is more than half of the pie, and it's a lot bigger than these two put together. But again, we're not stupid. We understand how to count. We can understand what a percentage is and what a count is. We don't need this. So, unfortunately, you're not allowed to do this either. This is a combination of distribution table and histogram. This is my other favorite in the book, a polygon. This is a frequency polygon. I know what you're trying to do here. You're trying to do a bar chart without making it look like a bar chart. Because I've seen this before. That's all you're doing. I know you're being sneaky. You're like, oh, I'll get a bar chart in there. Change the name, take away the bars. Boom, frequency polygon. No, it's just a bar chart with a line on top. But I can understand this. If there's one thing that I can't say you're not allowed to do, I'll give you the stupid frequency polygon. Because the frequency polygon looks a lot like we're talking about the shape of a distribution. And that's something that'll actually be handy for us. Oh yeah, your thing about the axis, yeah, people screw that up all the time. This is the correct axis, where you go the full range of a percentage from 0 to 100. And in this chart, it looks like that Democrats, Republicans, and Independents are fairly evenly distributed. I don't know how you can have like 150 something percent, but okay. Maybe we let people pick more than one. But when you change the axis and you're trying to show that there are more Democrats than Republicans, if you just do the range of values, I have a statistical program that does this automatically, and it's like, you guys just charged me $300 to make crappy bar graphs, and it does it by default, so you always have to go in and tell it to use the full range of X or the full range of Y. It's annoying. So this is bad. A, it's bad because it's a bar chart, and B, it's bad because it's a deceptive bar chart. If you have to, always make sure that your axis has the full range of values. All right. So we're pretty much clear that you're allowed to do two things. Right? You're allowed to use a frequency distribution table, and if you absolutely have to understand what a distribution looks like, you can do something like this, a frequency polygon. Or, if you have an easy way of doing it, a bar chart. But only if and only if you promise that you use it for the shape of a distribution. And you put the bars next to each other in order, like this one. If and only if. Okay. Because when we talk about our data, we want to understand how it's distributed across the range of values. One of the things we commonly want to know, what is the modality? What is the most frequent, most common response? Which has the greatest frequency of occurring in the data set? And depending upon what we're doing, we could have data that has multiple modalities. So if it's unimodal, uni means one. If it's bimodal, it means two, bicycle, bimodal. And multimodal just means got more than two. Could be three, could be five. We have lots of, if we do out religion, and we do a distribution of religion, we'll probably end up with a multimodal distribution. You're not going to have a lot of Satan worshipers and Pastafarians. But if you actually include the ones that people have heard of, you'll have multiple modes. What do you call a distribution with no humps? Remember, I'm a dad? It's a great dad joke. It's a horse.
Yeah, I get it.
There you go. One hump. All right. Actually, if it's a zero modal, we call that, of all things, flat. Because it'll look like this. Had to do a dad joke. All right. So we're going to look at our distributions. We're going to see what kind of shape they have. If it's great, it'll be unimodal. Also, what would be really nice is if the distribution itself was symmetric. If something is symmetric, it has a midpoint that allows you to fold it on top of itself. And I can verify that, in fact, symmetry is taught to you in at least first grade, because I had to do symmetry homework with Abby last year. Give her a shape, she draws the line, fold it over, see if it works. Symmetry is one of these weird things that we value. I went to a college whose campus was symmetric. We had a rectangular academic podium, which had like buildings on top. And then we had 4 student quads. That were also like a podium. And each quad had a high rise in the middle. And they designed this in like the 1960s. And then we had to add on a new library. Where do you put a library when you were only going to build one building? In the middle. So that way our campus was still symmetrical. It was really weird. It was really, really, really weird. And they named, this is the other thing, they named the quads. This was Indian quad, this was Dutch quad, this was colonial quad, and this was state quad. And they did it in the order of what New York State was and how it was inhabited. The Indians were there first, and then the Dutch came, and then it became a colony, and then it became a state. Really weird. Yep, this is SUNY Albany. Actually, it's Albany at SUNY. They don't like SUNY, eh? Guess where we put the fountain? Put it in the front. It's the bus loop. And oh yeah, the whole campus is a giant circle, by the way. No, it was confusing as hell because it all looked the same. It's like, yeah, when people in Edwards are like, I don't know where the room is. It's like, well, it's a big rectangle. Just keep walking. Eventually you'll find it. All right? Imagine if your campus was like everything was poured concrete columns in a square. It was fun. Okay. Again, we value symmetry for some reason. Ladies, symmetry is why you wear makeup. Gentlemen, they're just trying to trick you to think that the left side of their face looks like the right side of their face. Why that's important, I have no idea. Still haven't figured that one out. Mm-hmm. Pretty much. Okay. So symmetry is also something important to us in statistics, because for us it tells us how our variables are distributed and whether or not there are more observations in one area versus another. So ideally we want it to be symmetric, or conversely we want to know and be aware if it is asymmetric. Now, asymmetric, you can be positively skewed if you have more in the positive direction. Because this curve, if it were symmetric, would be like this. If the tail is towards the negative side, that's a negatively skewed distribution because there's more of the observations towards the negative side. Make sense? It's kind of counterintuitive. But you're looking for, because your mind is thinking, well, actually, most of the variables are over here. Well, your mind is thinking that because you're assuming that it's a symmetric distribution. But actually, there's a lot more area or a volume of data out here towards the positive side. Even though the height of the curve is lower there, that's still data. All right. Finally, looking at the distributions. We've mentioned this before when we're talking about modals. The height of the distribution is a representation of its variability. If a distribution has a sharp peak, that means most of the data is in a small area. So there's not a lot of variation in your data set. If you go into a college classroom and you ask the students, how old are you? You're going to get a smaller range of values, right? I'm going to hear a lot of 18 to 26 in the classroom. You're going to get a lot of that. You're going to get some of those Scholars Academy kids, and you're going to get people coming back to school. But for the most part, the core, the middle, the peak, is 18 to 26. You go to a Pelicans baseball game, you're going to see people all the way from babies to the ancient folks. I went to a lot of Pelicans games this summer. A lot of Pelicans games. There were people there of every age. Now, I'm not saying there might be a couple of bumps, because, you know, on Thirsty Thursday, you might get a bump. Or Saturdays, because Saturdays are for the boys. Stupid thing. All right. But for the most part, this is going to be flat, because you're going to have most of the ages represented, and if you're a parent, you're going to bring a kid, so they kind of offset. If you're old and you still have a spouse, you'll bring that person too. Okay. Bring the family, you got grandpas, parents, and kids. You're spreading that age distribution out, fairly equal numbers. Old people got nothing to do. They can sit and watch. It's good for old people. All right. So that's a flat distribution. No one mode that sticks out. Perfection for us in statistics is this thing. It's called a normal distribution. This is perfection. This is that Greek symmetrical model that fits Da Vinci's proportions. Because this normal distribution is unimodal. It has to be unimodal if it's good. Well, it doesn't have to be, but it makes it our lives easier if it's unimodal. It is symmetrical, and it's neither peaked nor flat. It's got a nice sort of curved roundness to it. It shows us that it does a wide range of values. This is also commonly known as a bell curve. Now there is an equation that gives us this curve. It gives us this shape. And if I show it to you, you all freak out. Because there's some stuff we haven't talked about beyond addition, subtraction, multiplication, and division. There's a logarithmic function in there, that kind of e to the something power. And that's got a nasty fraction in there. But essentially what we need to know is that the shape of the curve, its flatness, and its width is derived from two numbers. The mean, which is our measure of central tendency, and the variance, which is a measure of the spread. Mean is chapter 3. We'll do that next week. Variance is chapter 4. We'll do that in 2 weeks. And that's where we're headed. Because this curve is going to be really important to us. Like, so important to us for the rest of the semester.